Welcome back to the Demystify Sci podcast. I'm Anastasia.
I'm Shiloh.
And today we are digging into cosmology. As many of you know, we are planning a big event in Portugal this summer called Beyond the Big Bang. And we really are working on making it into a reboot of the grand traditions of the Royal Society. And what that means is that instead of it being a conference where we get together and it represents a single paradigm, we're bringing people together from all corners. We have plasma cosmology, we have variable speed of light, we have Machian cosmology, we have applied cosmology, we have
standard λCDM stuff as well.
And the standard λCDM stuff is actually really, really important because we've clearly expressed many times before on the show that we're a little bit skeptical about these paradigms. But I think that it's really valuable for us to hold this event, not just with a bunch of people that criticize the extant models, but with those that also know what those models actually are at the deepest level of detail and who can represent what parts of them are fragile and what parts of them are not. And so as part of the roll-up for the conference, what we're doing is we're hosting conversations with all of our invited speakers. And so today with us, we have Indranil Banik, who is an early career cosmologist at the University of Portsmouth, who works, I would say, in paradigm repair. Like, he recognizes that there's something that's not quite right in lambda-CDM, that there's a bunch of pieces of the model that aren't really fitting together. And so we sit down with him to, A, get a really complete picture of what the field looks like today, and then to start the ball rolling on examining some of the critical assumptions.
Yeah, we're going deep into all of our favorite problems with lambda-CDM today, but we're learning more details about why does mainstream cosmology think the things that they do. So that's really interesting. And by the way, if you want to join us in Portugal this summer, we would love to see you there, and it's going to be absolutely incredible and historic, not to mention being a beautiful seaside resort. So if you want to find out more about how you can become part of that, check out this link up here. And
if you're on the fence at all about coming and you want to see if you can negotiate with us a little bit to help out and see if you can get a little bit of a cheaper ticket, reach out. We're very flexible. We do need some hands on deck. And so if you have skills that you can barter in return for attendance, let us know. We're very, very open to that.
Maybe you can't make it out to Portugal this summer. Hope you can. But if you can't, maybe consider supporting the podcast through our Patreon site. So that's patreon.com/demystifysci. For just a couple dollars a month, you can join the conversation. We get together with patrons once a week. It's rapidly becoming one of our favorite hangouts on the internet. And I would love to see you there. So check it out. You can come over to patreon.com and check out one of our chats and see if it looks like a community that you'd want to be part of.
And then we have something else that we are planning. We have many irons in the fire right now. And that is a new segment called Paradigm Drift. Paradigm Drift is our attempt to democratize the world of theorizing. So you or somebody that you know and love might have a really cool theory of the world, but they don't really have a place where they can put it and get eyes on it. And so what we're doing is we are opening up the stage to you. Everybody has 60 seconds to present an original theory, after which point Shiloh, myself, and our esteemed panel member will interview them about the idea, how they came up with it, why they think it's going to change the world. And you can sign up for a chance to be part of that show in the description or right here at this link. There's no guarantee if you sign up that you will actually get to present. We will pull maybe 5 to 10 names out of the hat the first time that we do it. And so sign up again if you don't get your chance this February 20th at 6:30 p.m. Pacific. And if you want to come and see the chaos as it unfolds, check out the link below and you can attend and be a part of history. And for now, enjoy the conversation with Indranil, and we'll see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
So what was the project? You're having some seminar students try to put a lower bound on the age of the galaxy?
Yes, exactly. There's a large sample of stars which have like ages and uncertainties, typically within about a kiloparsec of the sun. So this must be from sort of detailed spectral analysis. And
This is just
Yeah,
based on like, can you tell us how they figured out the ages? Is this from the elemental abundances in the stars, in the spectra?
I think you have to analyze the spectrum in some detail, and some of the features change with over time as the star ages, if I understand correctly. I'll need to look more into how exactly you find the ages of individual stars.
Yeah, that'd be really interesting.
Yeah.
Do you know?
I would assume, I have never done this myself, but I would assume that they're looking at whether, well, first of all, whether it's a first or second or third generation star based on its spectral fingerprints, and then going off of the main sequence model for how long it takes stars to, live out their lives on average in some sense, so that you can get second or third generation materials to make the star from in the first place. And then other than that, yeah, I would assume that the difference, I mean, obviously stars that are aging off the main sequence according to the standard model, like stars that are moving in the red giant vicinity or
I
far.
think they're much easier to get the ages for.
Exactly.
That's true. There was one paper which just looked at a very small number of objects with like very precise sort of ages, and in that case, yes, it must have been the stars near the end of the main sequence lifetime. I don't know if that's what they did in this study, where they had about 320,000 stars in ages. Sounds like you couldn't find that many stars which were just in the final phases of their life. But maybe that is what they did, because you have very large numbers of stars nowadays that have been observed.
Yeah, the amount of data must be just, it kind of blows my mind sometimes. Austin and I are talking about this. We're like, obviously cosmology's got a lot of decisions in front of it as a whole, but my God, the amount of data that's coming in every minute. If you think of all the telescopes that are turned on 24/7 around the globe, it's like unbelievable just how much work can be done off of this data. Even the role of different LLMs in mining all that data, like it just seems like this isn't just for cosmology and astrophysics, but for so much of like medical science, the amount of sequencing data that's piling up. In general, like it seems like we're in this age of warehousing data at this point.
Don't think people are using sort of machine learning approaches too much just yet in cosmology. One thing that is important with some of these data sets as well, that actually also applies to smaller data sets, is the role of sort of preparing the analysis procedure like in a blinded sort of way, with sort of fake data, if you like, or indeed with sometimes it has to be with the real data where you've like injected some additional some extra feature into it, so people don't know the actual values that you'll get in the end, and those
like encryption of some sort.
Yeah, I mean the thing is, so for example, like you give people, so if they have to like apply various corrections to the data, for example, to find the Hubble constant, they have to get like distances and redshifts. But let's say like all the so-called distance moduli, some random number is like added to all of them, and then it's given out to the scientists to try and sort of get their best estimate of the Hubble constant. So, but that way they don't actually know what the real value of the Hubble constant is in their analysis, because they know that essentially it's been multiplied by some random factor, which they don't know what it is. So what's done, like they make all their analysis choices, and then at the end, the person who's in charge of the unblinding says like, okay, but what we actually did is we multiplied like all the distances by some factor. So according to like this consensus of how the analysis should be done, you got H naught of like 81, but because we multiplied it by 1.1, it should be like actually 72. So your analysis is actually indicating that H naught is 72. What that means, the scientists involved couldn't have tweaked the analysis to get any particular result, because they have no idea how changes to the modeling assumptions would affect like the consistency with particular hypotheses that they might have personally preferred or not.
That's so cool.
So
How long has
yeah,
that been going on
that's
for? Is that across all the journals, and is that standardized practice at this point? And how long has that been happening?
well, I mean, it can't always be done like that. But for some of the largest collaborations, yeah, this is starting to become the norm. There's not too many, like when big surveys publish results on cosmological parameters, nowadays it typically is blinded in this way. But it can't always be done like that. Sometimes it is just not really technically feasible. But I think people do this as far as possible. And in general, they place more emphasis on trying to get the methodology sort of clarified in a way that couldn't have been influenced by trying to get sort of particular results. So that's one important aspect. But in terms of the large amount of data, yeah, this is certainly helping. Though one has to understand that the actual amounts of data for some of the more distant objects still is limited. But yeah, it's getting more challenging. It's not like in particle physics where the amounts of data are sort of too large to store. Still, like most of the large data sets, like probably could store in like a single laptop or something. It's still not at that level in astrophysics that like we have so much data on distant galaxy you would struggle to store it. I think in the next decade or so, it might reach that point where it's a challenge storing and processing all that data. So analyzing it is expensive. Like already we are at a point, by the way, where with like the Gaia mission, for example, the amounts of data there are so large because you have like maybe 70 observations of each like source, and there's like a billion of them. We're already at a point where the Gaia missions collected data for 10 plus years. But the actual Gaia data release that scientists
Can you remind
use,
people what the Gaia mission is?
So the Gaia mission takes very precise positions of stars, generally in the Milky Way. And it does this about 5 times a year, I think, at least. And the idea is to measure the parallax of the star, but also its proper motion by seeing its sort of drift across the sky over multiple years.
And this is just a satellite that's just kind of plopped at L2 or something? It's just kind of traveling with us around the solar system?
It is, yes. But it's generated so much data that the actual Gaia data release that scientists can use now, the so-called data release 3, this only refers to the first slightly less than 3 years of data. So nothing collected after 2016. Of course, it's collected lots more data after that, but it hasn't really been analyzed yet. The next data release will be next year, but even that will only cover 5.5 years. So until like end of 2018, 2019 maybe. So still like much more data has been collected. To get the final, so Gaia's just recently stopped the science operations. That's after about 11 years. To get 11 years of data analyzed and out to scientists, certainly this will not happen. I don't think it's going to be done this decade. Probably be like the start of the next decade, in 2030 maybe. We'll get the so-called final Gaia data release. In fact, like the actual, for the Planck mission, we are in fact only just getting the final Planck release. That was like 6 months back or something. But this was launched in, I think, 2009, and it finished much of its work 4 or 5 years after. So yeah, it's creating these time lags, and in the future, an important aspect will be to try and minimize that. So you don't want situations where like you've got all the data and it's just not quite usable yet by scientists and for several years.
What makes the data as it comes out of a satellite or a telescope unusable? Oops, I switched to Shiloh. What is the fact that makes the data unusable? Like, is it theoretically possible to have a stream of just raw information that's coming off of some kind of detector that people could actually get access to and then see it from the start? Or is there actually...
I mean, certainly the people inside the collaboration are exactly in that position. And
Sure.
in principle, there's no reason why that couldn't be done for people outside it too. Often you've had situations where, like, with data releases taking so much time, you can ask people on the inside, like, roughly what does it look like, so they can plan. You can get things like that. But the point is that a lot of instrumental sort of corrections and calibrations need to be made typically. And it's about trying to pin down how exactly these things should be done. So, for example, with the Gaia mission, you look at the parallax of a star, and that's all fine. In theory, you want to just publish like the positions of it at different times. But what people do is they also look at a quasar where there shouldn't have been any parallax, and they try and work out like if there actually was, and how much of a so-called 0-point offset they should apply. So these kinds of things are what take time. You have to analyze the data in particular ways on a limited number of objects where you have confidence you know what they're actually doing, in order to calibrate the rest of the data.
Can I just catch people up who are not astronomers who might be trying to follow along this conversation? So, like, when you try to figure out how far away something is, you use this method called parallax, right? Which for people like at home is like a fun little experiment you can do where you sort of like put your finger really close to your face and close one eye and then close the other eye, like switch back and forth, and you can actually see your finger changing positions essentially. And then the further away it is, you put your finger way out here and you do the same thing, you notice that your finger doesn't move very much. So you can essentially gauge the distance by the amount of parallax, given that you know your eyes are a certain... Everybody knows their own eyes have a fixed distance between them, so your brain can do this calculation. It's basically high school level trigonometry. It's simple math to set up this series of right triangles where you can back calculate the distance from. So when we're talking about parallax, we're just talking about how far something appears to be. And then, of course, the nice thing about this satellite that follows the Earth as we make our orbit in the solar system is you have this huge baseline of the, entire, like, let's say diameter of our orbit, which is really useful for calculating this. So the idea of looking at something that's really, really far away, like a quasar, is that it's like when you put your finger really far away, it shouldn't really move much. So if it does, then something else is going on and you need to subtract that. I think that's kind of, is that a fair way of putting it?
Definitely, yeah. What typically happens that causes the parallax, we think, is some slight fluctuations in like how big the instrument is over a year because of the heating up and cooling down and expanded and contracted slightly. So it's like in your example, but if your eyes were to move apart very slightly, I mean, because the measurements are very precise, these things can matter. There's also other things such as, especially for the nearby stars, so many photons come in that it sort of saturates the detectors a little bit. And you get like electrons from one pixel like leak into the neighboring one. This
can you correct for that?
You can try to account for that, yeah. I mean, but it's definitely, it's starting to be a problem. I mean, with the Gaia, it's not as much of a problem. But people have had issues, like with the James Webb, for example. A lot of the most important targets to observe to try and pin down the Hubble constant, you actually can't observe with it because it like saturates the detector. So it seems like a very weird scenario to be in, where like the detector is so good that the structures you want to see would saturate the detector. But I don't. Maybe it's too good in that respect. But you can get into issues like that sometimes with the oversaturation. Sometimes you're better off like having something which is quite faint and like only slightly sort of excites your detector. But then you have very, very small numbers of photons. But sometimes it's much easier to deal with that because at least people know how Poisson noise works. So they at least know what happened. If you start like oversaturating a detector, this can be tricky to deal with.
Well, yeah, because things start to become really nonlinear through oversaturations. Like, so
Yeah.
in biology, we do Western blots. And Western blots are basically you take a protein, you attach it to an immobilized surface, and then you add fluorescent markers to it, and you expose it with film. And it's a way of quantifying the amount of protein that exists in your system. And you have to do all of these concentration gradients because you're trying to figure out where the linear range is. Because if you get to the point where you've oversaturated, like you have no real information about what's happening there because it's just this like huge blob and you're like, I don't know, it's a blob. Like, what do you want? But you otherwise can actually make very discrete measurements of intensity and concentration if you're within the right scope. So that makes a lot of sense because there's something about oversaturation that just breaks our ability to actually deconvolve what has gone into producing the oversaturation because it's like zero information is there past a certain point.
Yeah, this is I think I understand. It sounds similar. The other issue with space-based telescopes is so on the ground people normally calibrate the efficiency of all the pixels in the CCD, in the charge coupled device. They sort of typically look either at the inside of the dome or what works well is to look at the sky, but like shortly after sunset where it's still a little bit bright, or before sunrise would also work. But there isn't anything equivalent for a space mission. You can't do what is called flat fielding. You can't just take an image of a uniform sort of object that's sort of reasonably bright and find out how sensitive each pixel actually is.
You can't take a picture. You can't like just take a really filtered picture of the sun or something.
I think it's hiding from the sun.
No. You wouldn't be able to block out. You wouldn't be able to do
It's
that.
just
with
like
the
too
sun.
bright.
It's just too bright. As I was saying, like even some of the stars in the Milky Way can be too bright for the James Webb. But the Gaia, I don't know if people have had more luck flat fielding it effectively by observing simply so many stars scanning across the telescope. But it's still not like a normal flat field because detector sensitivities can change over time. So ideally, you'd want to sort of take a single image of some object that's reasonably uniform at every sort of night. I mean, this how people do things on the ground, or maybe not every night, but every week or so they do this. It just doesn't exist for space instruments.
It's really funny. I was just imagining somebody like launching the telescope with like a giant piece of paper that you could like put down in front of it so that it would cover the objective so you could actually flat field it. But I think that's highly impractical. What were you looking at?
I mean, I was hoping maybe to tie this back to the discussion of the Hubble constant that we dipped our toes into. Seems like those calculations depend on distance measurements and they depend on the redshift. And the cool thing about parallax is it's basically as close to a direct measurement as you can get for distance, right? So, this is the same method surveyors use on Earth to figure out how
it is
curvature.
very direct. Yes.
Right. But the problem is, I guess, like, not the problem. My question is when these people are starting to assemble these big maps, these surveys of distance versus redshift, we have to get into that weird world where parallax isn't quite as reliable, and so there's
You have to use a so-called distance ladder.
So this is where like the tower of assumptions and modeling start. This is where the inferences start to become indirect. But I'm assuming that those assumptions are kind of baked into the way like that data processing has to happen first, right?
There was one assumption that Indranil mentioned already, which is that when you're doing the parallax measurements, you're also looking at the parallax of quasars, which are assumed to be at a significant enough distance that they don't have parallax.
Mm-hmm.
That's true.
That seems to... So this is something that I don't understand. Are quasars just thought to be like in some ring around the circumference of the universe because they're representative of some like time period in the development of the universe?
They're not all at the same distance, but they're just very far away in all cases.
But isn't there a cosmological principle that says that the universe is kind of the same in all directions and in all locations?
Yes. So the distribution of quasars is indeed roughly uniform.
They just happen to not be like local. It's uniform, but at a distance.
I mean, distance and time get really convoluted in these discussions.
That's kind of what I was trying to say. Is like, is it some like representation of like eras? But I'm leading us down a psychopath. We can come back to quasars. You
I
made
think that
this
is
case
true. I
about
just
the
don't want
tower
to get
of
ahead of
Yeah.
ourselves, because I think there's something really interesting here, because we were talking about, wow, that's really cool that they've found a way to blind the researchers to the actual numeric values, but at the same time, those values, the data that they're starting to work off of, is processed through a number of assumptions in the first place, and that's really interesting. I'm also kind of curious, like, isn't calculating the Hubble constant pretty straightforward? Like, why would groups even come up with different numbers in the first place? That's a really dumb question, but I'm curious, like, what the answer
No,
would be.
I mean, the answer, of course. Okay.
I've never calculated the Hubble constant, so I don't know what I'm talking about. But
they shouldn't come up with different answers. But this is, as you say, like making various assumptions have to be made, and the idea is that different groups try and do these things differently and see if they still get the same result. So, for example, instead of using the Cepheid variables, they use the tip of the red giant branch and to measure distances and see if they still get the same result. You're right; they shouldn't be getting different results, but that's certainly true.
And I think they're all making basically the same assumptions in consulting this distance ladder, which, I don't know, it might be like worth like bringing people up to speed on what that means, right? Like, we obviously have this wonderful way of directly calculating distances in our neighborhood. But then the further we get away, we have to be more abstract in the way that we estimate distances. And
somewhat more abstract. I mean, what happens with the distance ladder basically is you use parallax to measure the distances to some object, which always has the same brightness, ideally. And you would know that they had the same brightness because in each case you are able to know the distance from parallax. So you can work out the actual brightness. Then when you see the same objects further away, the idea is that they will still have the same brightness, but in that case you can't check that assumption. You have to trust that they have the same brightness. And if you do that, then you could know the distance to those more distant objects, where parallax isn't possible. Typically, though, 2 rungs like this is not sufficient. One typically has to use 3 rungs in the distance ladder. So one has to, so it's like the same idea saying, but just applying it one more time. Typically, 3 rungs is enough. You can get away with 2 rungs now. Uncertainties become a bit larger.
Wait, let's talk about these rungs individually. Right? So, like, for instance, you're like, find a specific object that we know the brightness of. So this could be a star whose mass is known, and therefore by its temperature we could place it on the main sequence and determine its luminosity, its brightness, like you said, and then back calculate based on its apparent magnitude how far away it is. Like, basically, if there's a semi truck coming at you down a dark road, you don't know just by the headlights whether it's a bicycle that's really close or a semi truck that's far away, and so you have to back calculate this. So you could use, something like I just said, based off the temperature and its mass known from some orbit gravitational dynamics. But you could also use something like a variable star that's pulsating, right? Is that would you consider that another rung then, if you were able to do that?
Cepheid variables are one of the most important rungs, yes. So what we do, Cepheid candles they're not all the same brightness, but they have a very well-defined relationship between how long they take to oscillate and their brightness. And this can be calibrated very precisely because we can get trigonometric parallaxes throughout much of the Milky Way now. So there's many Cepheid variable stars which have parallax distances. Then the idea is to assume that Cepheid variables in more distant galaxies follow the same relation. So you would basically be able to. So this is, in your analogy, it would be like saying, like that larger vehicle typically has the headlights higher up or something. So even if you just see the headlights, but you also see like how far above the ground they are, then you can kind of guess how big an object it actually was. And then based on how bright it appears, you can guess how far away it was as well, roughly speaking. Cepheid variables can be thought of like that, that you, in a more distant galaxy, you can measure the period regardless of how far away it is. And
As
then
long as you're 100% sure that, this is a standard system, right? And it's I think there's like, it's worth mentioning, I know I brought this up before when we talked on the phone, but it's worth mentioning maybe that we've confused different types of Cepheids in the past. So Walter Beatty famously doubled the distance to many of these because they turned out to be two classifications of this. This was back in the 50s when people first started doing this technique.
One problem that happened is people looked at a whole sort of cluster of stars and they thought it was like a single star. You can get into issues like that. This is why it's important to check in to get distances in different ways that are not all sensitive to the same assumptions. For example, with the Cepheid, the issue of like crowding, which I think what you're getting at, where multiple stars that not at the same point, but they follow the same pixel in your camera, like that affects Cepheids, but crowding is a much less severe problem from some other techniques. So
I think there were just two populations that were being conflated as one, if I recall correctly.
Oh, yeah, there's also like a difference in like very long. Yes, there's multiple like period luminosity.
Well, there's just all these details, right? Stars are complicated, like this metallicity can affect the light curves for these two. Like it's very tricky.
But that's included typically, a correction for the metallicity is typically.
At this point it is, but I'm just trying to like introduce people to the historic challenges with this. Yeah.
Yeah.
So it's interesting trying to, improve these assumptions as you go along by recognizing things that and those things can wildly affect the interpretation of it. I'm so amazed by how far astronomy's come in such a short amount of time. Nasti was looking up the age of the universe across like 100 years, or was it 100 years? I don't know, but it was wild. I mean, it was like went from 3 billion years to 6 billion years to 10 billion years to, just the change that's happening in all of these disciplines as people refine those assumptions has been this breakneck speed that's hard to see in any other science, really.
Yeah, I mean, it's being able to measure some of these things for the reliably for the first time in some cases in the last sort of 10, 15 years. This is indeed a great deal of progress, and it can be confusing or it be difficult to understand the extent to which these techniques are reliable. I mean, to some extent, like even if a technique was reliable, if it's very recent, it still causes problems because it means there hasn't been enough time for other people to check it. Yeah, people do sometimes have doubts about the distances to some objects, but this is why we try and measure them in different ways. Like, for example, the so-called tip of the red giant branch, where you look at a whole population of stars and find some statistical property of it, which should always be at the same intrinsic brightness. It's much less sensitive to some of the issues that affect Cepheids. It has other issues, so there are other assumptions, but these are quite different. So in that way, we try and check if you still get the same distances, because this can also be calibrated in the Milky Way with parallaxes.
I wonder, with the way that you've described the data coming in, if there's a movement to like create primary data sets that operate on different assumptions, right? Because in other sciences, I feel like it's really, really uncommon for the person who's analyzing the data, who's analyzing the raw data, to not also be the one who's running the experiment in the lab. Like, I think that physics has that happen fairly frequently because of particle detectors and telescopes. But in general, like in my experience in biology, like I never got somebody else's data that they had collected, analyzed, and then sent over and were like, tell me what you see. It was always data that either I or somebody else in the lab had collected inside of an experimental system that we had developed specifically to test this thing that we were curious about. And so
But in astronomy, it's very crucial that other people should be able to like reuse the data in different ways to what it was originally collected for in many cases.
It's so unique, though.
it is. It's like it's incredibly unique. And I think that it would be good for this to be the case in the other sciences too, right? Like I think that in an ideal world, right, science would operate as follows. Shiloh's
There's
actually
kind of a cool story of how this got started in astronomy too. So like during the war, I don't know, there's 2 really nasty wars in the 20th century, but all the men, I guess, were away fighting, you know? And so the astronomy departments basically put the women to work doing all of the analysis and calculations. And a lot of the standard spectral classifications and stuff were developed by women because the men were worried about the women being in the cold, observation room, essentially. And so they're like, no, the men are going to like man the telescopes and then the ladies can process them. And they actually called the women calculators, which is kind of funny.
There used to be, computers.
Computers, sorry. They called them computers, I'm sorry.
Which actually, there was a very nice movie about this, The Hidden Figures, and they were showing how they used to do all sorts of crucial calculations for NASA before, like, computers were really, not necessarily invented, but before they were practically usable, and how they, when they were invented, and much more usable, how they transitioned to then coding the formally instead.
And so this is the route for the system where somebody collects the data and then somebody else analyzes it, and then like a third party will then perform secondary analysis on this first order filter?
I think like governments expect when they're funding a project, that a large survey, it's not just to address whatever science questions the researchers involved had in mind. Typically, the purpose of funding it is to generate a large body of data that can be used for many, many different applications. So it's very important that they document sort of what they did and create these data releases. There are rules sometimes where they get to sort of analyze the data and publish whatever they want for a certain amount of time before the data is made available. There are sometimes agreements like that. But the main thing is certainly it needs to be usable for other researchers, not in the collaboration, to test hypotheses that they've come up with. Actually, it wouldn't work very well if only the researchers involved in collecting the data could like understand how to use it. Because what I've seen is like with these large collaborations, they often it's very difficult for researchers to try and sort of propose very controversial ideas, because these collaborations typically have like rules about like you have to get it approved with multiple rounds of approval with senior researchers in the collaboration and things. And I was talking to some people at my institute about it, and there's essentially no way that anything very controversial would be published like that. But if the data was then made publicly available, which it usually is, then somebody else could try and test their ideas using it. And then it wouldn't be an official paper from that collaboration, of course, but it might still get through peer review, of course, but it would just be like a reuse of the data. Without this possibility of reuse, it would be very difficult to do astrophysics.
I guess the question that I have is, so it seems like one of the key aspects, because you're like the data gets released from the collaboration with a delay, right? You're saying that like the Gaia data is going to come in the next like few years. Still, like you're still waiting for the last.
It's already been collected. Yeah.
But there's some process of analysis that before it gets released to the community, there's like a set of assumptions that it's filtered through already. And I guess the question that I have is, how many different sets of assumptions does that data get tried with before it's released? Or is there one set of assumptions that it's released with and everybody just has to operate on the data that's been examined through the lens of those assumptions? Does that make sense?
Are the distance assumptions baked into the cake, I think? Or, because we haven't talked about redshift stuff yet, but we'll get to that. But I think that's what you're asking is like, are these latter?
Yeah, we've talked to people who have different interpretations of redshift, right? Like variable speed of light.
Let's get to redshift in a little bit. Let's
but I think that this is so. Let's
say
let's
stick with distance because we've talked about it. But yeah, are there
No,
people who have different?
Whether you talk about distance or redshift, like the choices made in analyzing spectra to like pin down the redshift of an object precisely, for example, these are not. People are careful that these things don't bake in any like assumptions or as minimal assumptions as possible regarding, for example, where the redshift might even be coming from, or for the case of distance measurements, like what the galaxy is sort of structured like. People are careful to just sort of publish measurements which just have the bare minimum of calibration type steps done. So I think like there are some exceptions to this, like in the Pantheon catalog of supernovae, there's many assumptions which relate to the cosmological model that have been baked into their sort of official release. And that is, by all standards, not good, of course.
So for other people who are just listening, like the supernovae are used similar to the Cepheids as a standard candle to gauge distances when we get further and further away.
Yes, right. But one major issue here is that if you were to try to calibrate the relation between the period and luminosity of Cepheids, there's many Cepheid variables in the Milky Way that can be used for this purpose. And you can actually do something similar in the Large Magellanic Cloud, one of the satellites, but it's similar, but it's like less rich in metals. So you can calibrate like how much that made a difference. So basically, all the relevant terms in what am I saying? All the relevant dependencies of the Cepheids' luminosity on period and metallicity, these can be calibrated like in a very reliable way. The problem with supernovae is because they're quite rare, one has to look out over a quite large region in order to get enough supernovae. And the region is so large that you don't have Cepheid distances to all of them. We only have Cepheid-based distances to 42 supernova host galaxies.
Out of how many total? Like what percentage is that? Roughly.
No, the total number of supernovae some supernovae were observed twice, right? But in terms of unique supernovae, there were 1539 in the Pantheon Plus catalog. So clearly, this is a very small fraction. So what goes wrong is if you can't really properly calibrate the relation between the supernovae are like Cepheids in the sense that they're not all the same brightness. If a supernova were to take longer for it to brighten and fade, typically that means it's brighter. And there's something similar with the color. So you have to calibrate the relation between the supernova's peak absolute magnitude or peak brightness and its so-called stretch and color. As they call the stretch refers to how long it takes for the light curve to rise and fall. But you can't really calibrate these things very well just using the galaxies where you have Cepheid distances. This can't be done just like that. So what you have to do is include lots of galaxies at larger distances. And at larger distances, because you're lacking a Cepheid distance, the only thing you have to go on is the redshift. And you have to make an assumption on what distance it is based on the redshift. And then, so basically it's a complicated procedure where you try and simultaneously fit the dependence of supernova peak brightness on its stretch and color, and also the cosmological model at the same time. So it's not really similar to the Cepheid variables where you can calibrate the period luminosity relation without really assuming very much.
And that's the funny thing about that distance ladder. It's like the higher you climb up on it, the more likely that your step's going to break underneath you.
Yes.
It's like it's a very dangerous ladder to use to paint your house.
And okay, so if I understand correctly, also there's like indirect and direct approaches to measuring the distance or the size of the universe? And don't they come up with different measurements?
Yes, there is. So this is the so-called Hubble tension, I suppose. What happens? So far we were discussing fairly direct distance measurements.
As direct as things get in astrophysics.
As direct as things get, the idea there is to minimize assumptions about like how you think the world works. I mean, you've seen some objects always have the same brightness, so you can assume it's true further away, but with minimal assumptions. Then you can also get the redshifts, which are typically much easier to get. And you can get the redshift gradient, if you like, the rate at which redshifts rise with distance. That tells you the expansion rate, because the idea is that as a photon's been traveling for longer, the universe has expanded more, so it's redshifted more.
Maybe we should, I know this seems super dumb, but we should probably explain redshift to people who aren't...
yes, so...
most people probably know, but let's just say it.
Okay. So the redshift is something that happens if you look at an object and you have photons coming from it. These photons get stretched. So an intrinsically sort of bluish object, it can look red, and there's various reasons why that's possible. But the most important one for what we're discussing now is that the universe has expanded in the time the light was traveling from that object to us. So all the photons have been individually stretched. So if you look at a spectrum of the object, for example, you see spectral lines at very precise wavelengths, which we know in the laboratory where the wavelengths at which those spectral lines should be. You can see that, well, you can observe them, but at a different wavelength. And in many cases, you can actually see spectral lines that wouldn't normally even be detectable with your telescope. Or sometimes there's spectral lines that should be detectable with it, which you can't see. And these things, you can work out the ratio between the original wavelength of the photon and the wavelength where you see it, of the spectral line rather. And in that way, you can work out, that ratio tells you 1 plus the redshift.
Basically, all your lines are going to be skewed towards the red in this case with this cosmic redshift. But redshift in general, like there's lots of sources of redshift too that are probably worth mentioning. I know there's ways of discerning between the two, but you can also have this Doppler-based redshift, right? Depending on the motion of one body with respect to the other. This is the one that people are probably most familiar with, is kind of the ambulance effect with sound, which is like an equivalent idea for redshift. It's as close of an analogy.
This happens, yes. Objects that are moving around. So that's actually a very useful technique to measure sort of how quickly galaxies rotate, for example, because you can see the redshifts are slightly different on different sides of the galaxy. And you also have gravitational redshifts. So if light's coming from near a black hole, for example, it'll look much redder. So these things all combine in the real world, and in the real world, it becomes very difficult often to be sure how much of the redshift is from each of these factors.
Can you tie?
Because you see like a total redshift.
Can you tie this back to the tension between measurements for the age of the universe?
Yes. So first of all, I'll briefly explain that, like, when we were talking about the redshift gradient locally, that's a sort of measurement of the expansion rate with some assumptions. The main one being that pretty much all the redshifts coming from expansion. But you could also predict it by looking in the very early universe and looking at some subtle features in the afterglow of the Big Bang, the so-called cosmic microwave background, or CMB. And that's in the very early universe, but you can extrapolate forward to today using the λCDM cosmological model, standard cosmological model, and that gives a different answer. So this, however, is obviously a prediction, right? And it doesn't agree with the observations.
Can I just catch people up on one other thing that I'm afraid might have gone missing?
Yeah.
The Hubble relationship that we're talking about, the Hubble constant, is essentially calculated, as you've gathered probably, from the redshift and the distances. But what it's really telling us is how much expansion is happening at what epoch in the universe, because distance and time are, like I say, very much married together in physics in general, but especially in this cosmological physics.
Oh, hold on.
So-
If it changes with epoch, shouldn't that be a Hubble variable then, as opposed to a Hubble constant?
The constant is kind of the slope of the line.
It's not the Hubble constant is not the appropriate term for it. It's actually scientists typically talk about the Hubble parameter because it's the rate of change of the overall sort of scale factor of the universe, which obviously isn't the same at all epochs. Typically, we are talking about the rate of change today because it's sort of easiest to measure. But it was different in the past. It was the Hubble parameter was higher in the past. But yes, you were asking regarding the does that answer your question regarding the tension between the early and late universe?
We're getting there. I'm just so like it seems like there are different approaches for measuring this Hubble constant, and based off of the approach that you use, you end up with a different term, which are only about, I think, 10% different from each other, but because of the specificity of the measurements, it means that they're actually quite different in terms of...
Well, I wouldn't call them different measurements, though. I mean, the local distance and redshift, so the local redshift gradient, that's the measurement, right? But using the early universe, modeling these tiny temperature variations in the cosmic background radiation, which is emitted when the universe was only about 400,000 years old, that cannot possibly tell you the expansion rate today directly. What it does is, in the context of a model, it tells you the expansion of the universe today, because that's one of the model parameters. So basically, you could find out, roughly speaking, you could find out how quickly the universe was expanding back then and extrapolate forward to today. This is not a measurement, it's a prediction.
Okay, so we have that there's like the CMB, that is the cosmic microwave background, which is the I look so concerned, which is the afterglow.
Sorry, we didn't even mention what the tension was between.
Yeah, exactly, and that's what I'm trying to get to, because like I come at this from the interested civilian perspective, and so I'm trying to represent that as best I can to the.
So I think the issue to understand here is that one can use a CMB to predict the Hubble constant, the expansion rate today. But that's like saying if you were to do some laboratory experiments to measure the gravitational constant, you have 1 kilomass, you see how quickly they accelerate or something. And then you say like, okay, based on like the properties of the Earth, it must have about this much mass. So there should be about this much gravity. And then you maybe adjust your calculation a little bit based on the actual gravity of the Earth's surface. And then you work out like how much the moon should be accelerating, how long it should take to go around the Earth. So that's all fine and good. So for example, you've got lasers on it to tell you exactly how far away it is. This is one way to calculate the moon's orbital period around the Earth. The other way is obviously to just try and measure or wait for between full moons, see how long it actually takes. And after many months, you can have a very accurate idea of how long the moon actually takes to go around the Earth. Now, but these are not two ways to measure the moon's orbital period around the Earth. Only one of these is an actual measurement. The other one is a theoretical prediction. But none of our theories can predict something like that from absolutely first principles. So they require observations to constrain, in this case, the gravitational constant. So you have to put in some other data to do that. But this data is not related to the moon, is the idea. So in the case of the Hubble tension, it is similar. You've put in data, but it's not related to the present expansion rate. It's related to the expansion maybe when the universe was 400,000 years old. And in that way, the model is able to predict the expansion rate today. But that isn't a measurement of the expansion rate today.
I love that. Okay, I think that's the best explanation that I've ever gotten for it. So thank you for that. And so, go ahead. No, go ahead.
It might not be the right time to do this, but I'm curious. You said when the universe was 400,000 years old. We haven't unpacked for people why you think that was a 400,000-year-old universe.
The CMB?
Just like he's just made references to these time points. And remember, we've only talked about distance in this conversation, and we've said that distance and time are related, but we haven't said why people think that it's a 400, that particular distance is a 400. Okay.
That's a good question. Certainly, in the figure of 400,000 years old does not come from any measurement either. That also is like a calculation you can make based on how much matter and radiation there is today, and various other. Sorry, not just based on that, but based on the temperature of this background radiation today. You can calculate like when a particular phase transition should have occurred in the early universe. And this is a transition between in the very early universe, it was so hot that you couldn't have neutral atoms. But eventually it got cold enough that the electrons started entering stable orbits around protons. You had neutral atoms. So there's no independent way to know that this occurred 400,000 years after the Big Bang.
Okay.
I want to clarify the distinction between like these theoretical calculations when you say like, this happened 400,000 years after. But that's in a model, as opposed to like, for example, the age of a star, where it's like it's not reliant on the cosmological model, and it's like, that star's 11 billion years old.
That's reliant on a different model, I guess.
That's reliant on modeling assumptions, but not cosmological ones.
Right.
Okay, so this is actually really interesting. So, why haven't they been able to tweak the CMB model in order to bring it in line with the distance lattice?
Local.
Yeah.
Like,
why is that? Is it just nobody wants to add the next parameter, or is it something more complex?
No. That is actually a common approach to solving the Hubble tension, but it is very difficult to work in practice. The reason is what you have in the cosmic background radiation. You have a certain amount of fluctuations in the temperature on different angular scales. And on some angular scales, there's more fluctuations than on other scales. So it's basically it's like with a musical instrument, like with a guitar string. What would happen? You'd get sound in principle at all frequencies, right? But then it would mostly come out at a fundamental frequency and at harmonics or multiples of that frequency. So similarly, in the cosmic background radiation, you have more power on some scales than on scales which are either smaller or larger. So if you were to plot like the temperature fluctuations against angular scale, it'll have these oscillations in it.
What is when you say angular scale? Can you break that down for me a little bit more? What do you mean by angular scale?
Oh, this is another really fun one for people too. The distances and angular separation are deeply related because it goes back to parallax, from what I understand. It's basically that same idea that the angle of separation is equivalent to a distance en masse.
But I specifically, I'm trying to, because the way that I operate is that I try to build, as you talk, I try to make a movie in my head of the thing that you're describing. And so I'm like, I have the curve of the CMB in my head, and as you talk about angular separation, I'm trying to figure out what is the process by which that's detected or applied or included.
So what people do is they look at the CMB, which is a 2D map of temperature across the whole sky, and they find out the extent to which they find out the extent to which 2 points separated by some angle have what the difference is in the temperature between those 2 points. So it's essentially a measure of how noisy the CMB is on a particular scale.
Got it.
Particular angular scale. In fact, if you look at the CMB, you can see that there's basically degree scales where there's the most fluctuations. That on very large scales, it becomes more uniform, and on smaller scales, it's also very uniform.
So, and tie that back to the analogy of the guitar string for me with the fundamental.
Yeah. So what happens here is these right. So the reason these the different angular scales correspond to different length scales, right? So okay, what actually happened with the CMB is you had density fluctuations imprinted like at the Big Bang. It's a very messy process, imprinting out of noise, and this created density fluctuations on like all scales, basically. Now, the important thing is that a density fluctuation that was created on a small scale, it would oscillate very quickly, whereas a density fluctuation on a larger scale would oscillate much more slowly. Now, what the so-called first peak in the CMB corresponds to, so that's the largest angular scale at which there's a so-called peak in the CMB power spectrum, or map of fluctuations versus angle. What this corresponds to is the it corresponds to a particular length scale such that in an initial sort of compression wave, an initial overdensity, evolves to reach maximum overdensity. So in the time between the Big Bang and recombination. What you have to understand is there's a fixed amount of time between the Big Bang and this recombination event, regardless of how large or small a length scale you're looking at. So what has happened is, so that's the first peak. The second peak corresponds to an initial compression reaching maximum compression and then reaching maximum expansion again. So it corresponds to that.
Shila's crawling around on the floor. He's trying to get a picture of the CMB. Yeah, because I'm trying. I think that this is actually going to be very helpful because as you're talking, I think I'm visualizing the wrong thing because I'm visualizing the black body curve of the CMB, but I think that you're actually talking about the map.
We're not. I wasn't talking about the spectrum. So I think I explained it in here. If that helps. Yes. So what we are looking at is the fluctuations in the temperature on particular scales. So basically, if you were to put circles on the sky with some radius, for example, like you look at degree scale patches of it, to what extent do different degree scale patches have different temperatures? But you can also play the same game with like 2 degrees or half a degree. Right, and what I was talking about in the CMB power spectrum is a plot of the temperature fluctuations versus the angular scale at which you smooth the CMB.
Which is kind of like what we're looking at in the bottom picture here.
Let's look at a much finer scale, yes. But yeah, this is a good sort of depiction. Although of course, with the limited resolution, I think this must be from Kobe. So
yeah.
The limited resolution here, you can't get results for super fine angular scales. It's simply not possible.
What do you make of this? Galaxy removal business? Like, do you think that you can get reliable kernelation? Like, can you actually see the anisotropy properly after you've subtract? Because I think that's what we're looking at here is the subtraction of the galaxies.
Yes,
loud black body noise that's kind of in the way.
The thing is, well, people have done analyses where they exclude, for example, the sort of equatorial plane you can see here, which is like the band of the Milky Way. But nowadays you can get fairly reliable subtraction of it because the Milky Way isn't so bright in the microwaves. And the black body, what actually happens if you, for each pixel in the CMB, if you were to look at a spectrum of it, you'd get like bumps from various contributions. And the CMB bump is very clearly defined as like an additional feature. Like in the microwave wavelengths, most of the photons are coming from the CMB. So you can easily see like exactly how high is the bump from the CMB in that pixel, and then compared to other pixels. So it's fairly accurate nowadays, even for lines of sight which have at optical wavelengths at least, which have a lot of stuff in them.
So can we go over this picture a little bit? Because there's basically 3 diagrams. One is this like very smooth color, yin yang, like bluish,
yes,
red
that's
and
the
purple.
dipole.
Then there's the one in the center, and then there's the one in the bottom. Like, can we just because I think that these things float around all the time, and
Yes.
I've seen them many times before, and I know it's the CMB, but I don't totally understand how all 3 relate to one another, and I think that it might be helpful to have.
So, maybe we can show them again.
Yeah, keep it. Yeah, let's keep it up. Okay.
So the first panel shows the CMB temperature across the sky, and you can see like a clear sort of dipole pattern. It's blue is hotter, I think, towards the bottom left, redder towards the top right. This corresponds to a simple dipole pattern, which is caused by the Earth's motion relative to the CMB. It makes the CMB hotter on the side which we're approaching, and appear cooler on the other side. So
Is that what is the phenomenon that causes that? Is that a thermal process? Is that a motion, like a Doppler type effect?
It's a Doppler effect.
Gotcha.
So this is not intrinsic to the CMB.
So that's got to be subtracted out first.
Yeah, that's got to be subtracted out first. In the second panel, that's subtracted out first. But the galaxy hasn't been properly accounted for, or the pixels haven't been analyzed properly. In the third panel, that's the most complete picture we have of the intrinsic temperature fluctuations in the CMB from different across different directions, accounting both for the galaxy plane, all the sources in there, but also for the Earth's motion relative to the CMB. So the bottom panel gives you as complete a picture as you can hope to get of of the temperature variations across the sky that come actually from the CMB itself, and not from like what happened to the universe later on.
And the angular the story that you were telling about the angular separation and the fundamental frequencies that are found at the small separation and the larger separation. Can you see that in this drawing, or is that something that's or in this image, or is that mathematically?
It has to be calculated mathematically. It's a bit difficult to see here. Well, I mean, you can't actually see it here because Kobe wasn't able to resolve the first acoustic peak in the CMB. Do you have like a picture of the the Planck CMB power spectrum? Maybe. Yeah, there we go. Yeah, and any of these pretty much will do, right? I mean, yeah, for example. So what you can see with any of these panels, what they show is the temperature fluctuations on the y-axis and the angular scale on the x-axis, going from larger to smaller scales. And this is like doing like a frequency decomposition of a guitar string. Like you can see all these nice harmonics, and you can see like almost 7 peaks now. What they tell you is they tell you in quite high accuracy the size, the distance rather, that a sound wave could have traveled between the Big Bang and recombination. But they don't just tell you that, they tell you other things about how much sort of visible or ordinary matter there was, how much dark matter there was. They can even tell you about how much dark energy there was, because that doesn't affect the CMB, but what it does is it can make the CMB more distant from us, and that can reduce the angular scales of all the features.
So you're like kind of talking about how lumpy the temperature is across the night sky, essentially, this background temperature.
Yes, exactly. It's
but I really think we got to back this up though, and like explain to people the story of where this radiation is supposed to be coming
Yes, sure.
I'm at this point I'm satisfied. I have answers to my question. Well, actually at some point I do want to get to that blackbody curve, but before we get there, let's do the story of the CMB and its origins.
Okay.
In terms of like cosmological origins of the CMB, is that what you were pointing to?
Yeah, I mean, just catch people up really quick. At least, like, what do people think this light is coming from? Like, how in the world do we have this light source that points people back towards this origin story?
So, one thing is, it's not really. I mean, it's pretty much uniform over the whole sky. So these temperature fluctuations you are seeing are only at the 0.001% level. So it's almost exactly the same temperature in every direction. And it's very hard for any astrophysical source to be that uniform over the whole sky. I mean, which certainly implies it's not correlated with our galactic disk. But also, like, there's very few things which are that uniform. Where we think it comes from is basically in the early universe when it was very hot. All the atoms were ionized, so all the hydrogen and helium was ionized. Electrons could come near an atom, but they wouldn't be on a stable orbit. They would get knocked out again. And what happens is all these free electrons floating about, they make the universe very opaque. So any photons going around the universe, they could be emitted somewhere, but they would be absorbed very quickly. Maybe re-emitted again, but generally in a different direction. So the universe was basically sort of foggy. So it's like if you had like in a sauna, it's like very foggy, but then someone cools it down, and at some point the water like condenses, and finally you can see what's actually there. So it's kind of like that. At some point, the universe, as it's expanding, each photon gets expanded, and that effectively makes it colder. So the universe is expanding; it's also cooling down. What that means is, at some point, it's cold enough that neutral atoms are finally stable. And when they are stable, electrons pop into nice orbits around them. And then there's basically no free electrons anymore. They're all bound to atoms, generally hydrogen, so just protons.
So this is like the creation of the first atoms.
It's the creation of the first atoms, yes. And then what happens at that point is the photons that were around at that point, they are no longer absorbed. So they can just, a very, very tiny fraction of them are absorbed, but the vast majority of them are no longer absorbed. They can just sort of shoot across the universe with basically negligible chance of getting absorbed anywhere. And because of that, we can see a sort of snapshot of the universe at a particular moment when photons were finally able to propagate more or less freely. So that essentially is where the CMB comes from.
Hey folks, remember this podcast is entirely supported by listeners like you. In other words, we work directly for you, but you need to actually throw down $1 or $2 a month in order to keep this thing going. So come over to patreon.com/demystifysci and check out how you can get involved. Otherwise, enjoy the rest of the episode.
So just thought I'd mention, like, in relation to your question about like why people can't alter the fit to the CMB and just use a different expansion rate and still fit the CMB. The answer is because, like, you saw the incredible detail with the power spectrum, including like 7 peaks and their precise heights and exactly which angular scales they're at. If you change the cosmological parameters, such as the expansion rate, it's simply not possible to fit it anymore.
That's fascinating. Okay, I love that. So, just before we took a break, we got to the point of where the CMB comes from, which is that
yes,
you have the Big Bang. After the Big Bang, you basically have this foggy, soupy period where there's no atoms yet, right? There's no hydrogens.
No.
Are there atoms?
No, that's right. There's no atoms.
And then there is recombination. Recombination is this condensation process by which the fog condenses into the light atoms that the universe begins from. My question is this. And then, and the CMB is the fingerprint of the photons that escape that recombination event that like aren't captured in that condensation. Is that fair?
Yes, I mean the CMB is those photons that aren't captured by atoms. It's just, all the photons just that were floating around then. At some point, they suddenly weren't captured anymore. At some point, the universe suddenly became opaque. So they managed to sort of go across the whole universe, essentially.
So my rudimentary understanding of like the source of photons in atoms or in plasmas is the jumping of electrons between orbitals, which produces the photon, right? Like if I take like a sample of sodium and I put it in a flame and it burns yellow, that yellow light is reflective of some electron transformation that's happening with the atoms, right?
It represents electrons jumping from one shell to another, yes. But it's not the only way to get photons. I mean, if it was much hotter, you could get, I mean, essentially how do I put it? The universe had a large number of photons flying around in any case.
But where do those photons, do we have, is there a model for where those photons come from? Or it's just like in the Big Bang produces photons and it's like the Big Bang is the mechanism by which photons are produced?
Right. So the Big Bang produced a lot of energy and some of it, okay, so basically there is a mechanism for it, which is to say the Big Bang produced a lot of energy and it then eventually formed into protons and neutrons in the same way as at a particle accelerator. You just you create a lot of energy at some point and you hope that energy converts itself into like a heavy particle, but perhaps it'll be a heavy particle that no one's ever seen yet. And that would be why people do these experiments. So it's the same sort of idea with the Big Bang. It had a lot of energy, it created particles, but it created like almost the same number of antiparticles. So what happened then is that these annihilated each other and that produced a large number of photons. And there was only a very tiny excess of matter over antimatter. So in case you're wondering, like, where did all these like free-floating photons come from? The answer is it came from the annihilation of matter and antimatter. And actually, there's only a very tiny excess of matter over antimatter. So what this meant is that for every proton, every nucleus, if you will, there were about 400 million photons flying around because the cancellation between matter and antimatter was almost perfect. So the real question is not really where did all the photons come from, but where did all the matter come from? Or more precisely, why wasn't it annihilated with antimatter? Because there should have been about the same amount of antimatter. And in the early dense universe, there would have been plenty enough time for them to sort of find each other and annihilate each other.
So up until this point, I've been with you, but it sounds very sci-fi at this point. Is it widely acknowledged that this is like a sci-fi version or like a sci-fi-y sounding version of the birth of the universe? Or is antimatter as a motivating, or I guess the annihilation of matter as it combines with antimatter at this point, like fully well established? We see this all the time in laboratories, and we
do, yes.
Okay. And what is
the existence of matter and its annihilation with antimatter are very well established. What's not very well established actually is the asymmetry between them. There must have been some reason why the two aren't exactly the same. But what I was describing is the standard picture for this.
Do people do these matter-antimatter annihilations and get blackbody spectra in the laboratory that look just like the CMB?
They don't, not from an individual interaction, no. But if you have like many different interactions, many different particles and their antiparticles, but also remembering that these wouldn't all happen at the same time. So if they happened earlier, then they would have been, the photons would have been redshifted more. So because of the Blackbody spectrum arises as it's a result of many individual sort of processes which are and it's like a statistical distribution. So kind of like the Gaussian distribution. Like if you were to take a single measurement of something, often it's not it doesn't lead to a Gaussian distribution. But if you were to then take like many instances of that measurement and then find the average, that would, and then you were to repeat this like multiple times, find the average like again and again, then these average values would more or less follow a Gaussian distribution. So it's kind of like that.
It's kind of weird though, because it's like it's not a Gaussian distribution, like it's a particular Planckian thermal.
It's an analogy. Like it's in this case it's not a Gaussian, but that's mainly because there's like, I think a Gaussian is what you get like in one dimension maybe, but in 3 dimensions, like, well, we know the distribution of particle velocities, for example, will follow a Maxwell-Boltzmann distribution. So it's roughly speaking, it's like that. I mean, how to explain it? Yeah, it's because of having a large number of individual sort of random events. It leads to a certain statistical distribution. Certainly, if you were to collide like a particle with its antiparticle, it would generally produce photons at like a particular energy, right? It corresponds to like the mass of the particle, because you get generally 2 photons emitting in opposite directions. So you wouldn't get a Blackbody spectrum from that, certainly. But if you had like many such collisions of different particles at different times, with different amounts of energy in each case as well, because sometimes they're colliding, it's not, they're also putting in the kinetic energy.
I think you definitely get a Gaussian of some sort, but like my question is, the Blackbodies are particular fingerprints, right? So, you know, the reason they call them Blackbodies is they like took these soot-covered chambers and essentially heated bodies inside of them until they're at thermal equilibrium, and they actually put a prism up and measure the distribution of frequencies, and it's kind of this rainbow of colors essentially, right? And the peak color can allow you to back calculate the temperature of that black body or the object that's inside of it in thermal equilibrium. And so it's like this really interesting way of measuring the temperature from the light of heated bodies, which is really interesting. But it's never used to gauge the temperature of heated gases in a laboratory or heated particles. It's always bodies, right?
And hold on, I want to. Well, actually, no. Go ahead. I haven't.
But what I'm saying is, that's because there's typically not in a laboratory. There's typically not enough space for there to be like enough sort of randomization to make a Blackbody. In a star, however, that does actually look very much like a Blackbody spectrum.
Oh, stars are beautiful Blackbodies for sure. Yeah. But,
okay, so hold on. Before we get into the question of the stars, which I'm like, so with the Blackbody spectrum, I understand the Blackbody spectrum to be produced by a solid object as a kind of like readout of the material itself resonating, right? So it's like if you hold on, I'm not saying like I'm using the wrong words. So it's like if you have a gas and you have a single electron jumping orbital levels, that produces a single color of light. But if you all of a sudden have a lattice of atoms, and inside of that lattice, you're getting a lot of, you're getting the transitions that occur, but they're spread out through the lattice, and so it creates this Blackbody shaped smear. Like a lattice where the electrons are transitioning produces a Blackbody, because I think, like, this is the only way that I can imagine it as producing it, because of the various, like
There's like lots of different
non-local
energy jumps available, right? There's lots of different
Yes, that's
energy
the
Yeah.
key
jumps.
thing.
Okay. That's what I mean by
It- it-
resonance. I think resonance is the wrong word. It's
It might be,
harmonics.
but
Harmonics.
resonance maybe, but the point is there's many different of them available.
Exactly.
So because of this, you're able to generate like a very broadband spectrum. I mean, maybe if you certainly if you had a reasonable size black body like on the ground, if you looked at a spectrum in great deal of detail, you would see perhaps the individual lines that contribute to it. Maybe if you were to zoom in super precisely. So it wouldn't, of course, be a perfect black body, right?
You might have to zoom to the level of like a countable number of atoms to start to see into
Something like that, maybe.
right. Like if
So
you
you might have to zoom in very, very far. Yes.
yeah, like I think that probably by the time that you get to like something that you can see with the naked eye, you're probably like well above that level. Maybe.
Yeah, I mean, I think you'd be hard pressed to see.
Because like a tungsten filament in a light bulb is a very thin filament, but that's
But you can still
continuous.
fairly close to black body. Yes.
Yeah.
So yeah, you don't necessarily need. Well, I mean, a macroscopic object still indeed has, of course, very many atoms.
Yeah,
So
exactly.
maybe by that point you're already in the regime where it's very close to black body.
God, I'd never thought about that. I'm like, what is the minimum number of atoms that you need in order to create a black body? That's a really interesting question, because then you also can ask the other question, which is, okay, well, how many of these gaseous interactions do you need? Like, I'm trying to say this, like, if inside of a lattice you can have X number of interactions that produce a continuous Planckian spectrum, like the perfect black body spectrum, then there probably is some calculation that you can make through statistical mechanics to say, like, how many atoms do you need in order to also produce a black body from the sheer number of
I don't
linear
think the number should give you the same fingerprint necessarily. I don't see any reason why that would be the case, why the frequency distribution would be the same just because you have a bunch of atoms. I mean, all right, so
Because
this
then
is...
you'd need compositional differences, right? Because like if in a gas you have lines of a given frequency that
Yes.
produces the spectrum.
Usually very discrete set of lines for any given gas under
Exactly.
given temperature.
So like
pressure.
sodium is the easiest one for me because I can see the single yellow line. I'm like, okay. So if all gases can produce black bodies, then at sufficient density and heat and pressure, then that means that yellow, can you make a cloud of pure sodium gas produce a perfect black body theoretically?
I think so, but it would need to be hot enough to be like completely ionized. It might have to be a plasma of sodium nuclei basically flying around, perhaps, along with electrons.
It's never
it
been
might-
done. We can say that
Yeah,
much.
like all the plasmas on Earth when they do this look real lumpy. Like if you look at a
Yeah,
plasma,
so I think
it has to be unimaginably huge.
I mean, it's a little bit of a leap. It's a little bit of a leap. I mean, maybe, but like, there's no evidence that that's possible. Except he pointed to stars, which is, So just to like build this out, what we're talking about here is that the early moments of the universe are supposed to be from this ionized state, right?
Mm-hmm.
And so I was like, that's kind of interesting because we've never been able to see a black body spectrum from ionized gases in laboratories. And fair enough, he says, like, we don't have enough of them, but we do in stars. And so why do you think that the stars are ionized plasma?
What do you mean? Why do I think they're ionized plasma? I mean, at those temperatures, it would be ionized, I guess people have looked at the composition of the sun and they have a good idea. But not everything will be ionized. Some of the heavier metals may not be fully ionized. But by looking at the strengths of different sort of transitions between energy levels, we can find out what the temperature is. And, lighter atoms like hydrogen and helium would be ionized. So that gives us an idea of what is happening at the surface of a star.
I mean, the phase diagram gets increasingly complex as the years wear on. So, from what I understand, like when the gaseous model of the sun was built, it was a very limited phase diagram that was understood. I believe it was Andrews who did the original phase diagram work that essentially showed like no matter how much you pressurized hydrogen, it was going to stay a gas. But we found these like weird metastable forms of hydrogen now in the liquid region, right? They're being attributed to the depths of some of the gas giants and so forth.
Yes, you get liquid metallic hydrogen, as it's called, that can happen at extreme pressures.
Which is like really poorly understood. I think there is some indication that it could be metastable though, which means that it could potentially exist if formed at a higher pressure and then rise into a lower pressure and still remain stable. I just find it.
I think, look, Shaila's driving at something that's really straightforwardly simple, which is that there's this assumption at the very heart of physics about the ability of gases to produce blackbody spectra, which is oftentimes demonstrated as being transparently, obviously true by pointing at stars. And so if stars, which are gaseous, produce blackbody spectra, there's no problem. Because they're gaseous, they're producing blackbody spectra. Obviously, like everything's tied up in a neat bow. The question then becomes, what if our models for the composition and structure of stars deserve to be updated in parallel with our understanding of a different phase diagram for the hydrogen that's inside of the stars?
This will only affect the deep interior of the sun.
Unless it's metastable, right? Unless that liquid metallic hydrogen is metastable.
Can rise to the surface, you mean?
Yeah, exactly. I mean, you gotta admit, like there's definitely a gaseous plasma in the atmosphere of the star, right? We can see these beautiful plasma lines and everything, but the surface, or whatever we want to call it, the photosphere, has this almost perfect black body. I mean, it's not perfect, but it's almost perfect. It's a beautiful black body spectrum to it. And just in light of the fact that the only things that do that for us in our own experimental hands seem to be liquids and solids, in other words, bodies capable of forming either transient or permanent lattices, it seems like there's something going on there that could be interesting, especially as we come to understand more and more about liquid metallic hydrogen, which has been a brand new science, especially getting that, being able to actually capture a picture of that phase at such ridiculous pressures and so forth.
Dumb question, but I think I remember hearing whispers that like Jupiter is thought to be large enough to contain liquid metallic hydrogen. Is that?
Yes, it should be. It's thought to be, yes.
Okay, and so like if it's possible in Jupiter, then is there any reason to think that it's not possible on the sun?
I mean, I don't know enough about the structure to know, but in Jupiter, like you don't have heat as such coming out of the interior in the same way from fusion reactions. So I think what happens in the sun is it's not the temperature in the interior is hot enough that you can't get into this liquid metallic phase in the sun. That's my understanding, but I don't know if what exactly the deep interior of the sun will contain. So at least it will contain fusion reactions, though, which makes it different to the case of Jupiter.
I think it's really interesting to realize. For me, it's really interesting to realize how it's like, because astronomy and astrophysics are kind of referential disciplines, it feels like there's like, this is kind of like what we're trying to get at with the conference and everything else, which is that like everybody's kind of aware that there's tensions in the models, right? Like there's some things that work, there's some things that don't, and there's this like huge diversity in how much people are willing to impugn the existing models, right? Because I think that for some people, they're like, well, they're a little bit off. They deserve some tweaking, but they're like, mostly like pretty close. And then there's like another school of thought who's like, our understanding about stars is completely wrong. This is a model that explains like how stars work where they're not actually gaseous plasma. And that requires us to rewrite literally like every single conclusion that we've made about astrophysics from spectra and CMB stuff for the last like 60 years. And I think that kind of everybody exists between those two poles.
Yeah.
And
there's a huge amount of specialization too, right? Like you've been through the academy before, right? Everybody's depending on somebody else to tell them about some other aspect of the superstructure, right? Like of the overarching knowledge base, like it's very interdependent, right? Nobody has the depth, the complete depth on any particular topic.
That's a really interesting question. Okay, so how many people do you know that you work with who you feel have a grasp of the abstraction, like a full grasp of every abstraction layer that goes from basically like quantum phenomena all the way up through the biggest cosmological phenomena? Like, are there people walking around like that have like a full model of quantum physics in their head and also understands like all of chemistry and also understands all of astrophysics, and they're just like, it's just this like teeming roil in their mind of all of these concepts? Or do you find mostly that people specialize with some dalliances into the depths?
Mostly people specialize. I think like the one thing to understand is in the standard cosmological model, there's ingredients which don't have a proper basis in quantum theory. For example, like the standard model of particle physics, right? It doesn't contain dark matter, for starters. So yeah, it's not possible that anyone has like an understanding going from a deeper quantum theory to an understanding of the whole universe. But I guess it's also impractical in any case because the complexity would be so high. Certainly in my experience, like people are typically just they're experts in one area and they are reliant on other people, experts in other areas typically.
Okay, and so the next question that I have is like, is this something that we should expect to be possible, to have something that is fully continuous from quantum phenomena to the largest astrophysical phenomena? Or is that a kind of naive read on the what's fair to expect from our understanding of nature?
Well, it's definitely fair to expect that because I mean, it's not like anything magical will happen at a particular scale. So what has to happen is there has to be like a continuum of behavior. It's like saying, like, will there be a quantum theory of gravity? Can we sort of expect that to be possible? Now, obviously, you have both quantum mechanics and gravity in the real world. Obviously, you know, a system is not going to do something magical if both are significant to it. So, for example, if you had a small black hole, it's got to do something, right? Maybe it'll explode very quickly. That's what our theories seem to indicate. But nonetheless, it will do something. It can't just be like a. I mean, our maths might break down, but the object will behave in some particular way. So clearly, it's reasonable to expect a theory which can handle that. Nature must be able to handle these scenarios. It's not going to just give up. I mean, even if we do. So it's definitely reasonable to suggest that ultimately there will be some explanation going from quantum mechanical scales all the way up to the cosmological scales and everything in between. Because whatever scale you pick in the middle, I mean, nature's got to behave in some particular way on that scale, even if our equations can't handle it.
Mm. And so, like, go ahead. And so I guess when I look out onto this landscape, and I don't have a dog in this fight, right? Like, I come at this from the perspective where, you know, the textbooks all say one thing. They're like, this is the Big Bang, and this is how it happened. This is, like, how the CMB relates to it. This is the statistical mechanical explanation for how blackbodies are formed from gaseous plasmas. And then on the other side, there's the people who are like, well, hey, there's all these things that are wrong with that. And I sit in the middle and I watch both of them, and I'm curious to know if you have a sense of whether or not people are interested in revisiting the assumptions that have gone into these fundamental models, and like and are people interested in attempting to see things with a different set of assumptions, or is there a sense that it's just like not necessary?
I mean, another way to expand that question might be, what are the areas in which people are doing that? Like, there might be other areas, right, besides the CMB.
Yeah, it's like, okay, so
Like you just put on a conference, right? Or you're planning one yourself, right?
Yes, a part of the National Astronomy meeting will be discussing the Hubble tension. Yes.
so like if you will pardon me a flight of fancy in a completely different direction from astrophysics and cosmology into a field that I'm much more familiar with, which is biology. Like there's a guy, his name is Michael Levin. He's a professor at Tufts. And I don't know if you've seen his work floating around, but he basically he devised an experimental system where he could take a flatworm that regenerates. And normally you cut the flatworm in half, and then you regenerate and you get two perfectly happy flatworms, because this is, the planaria is just able to do this. It's inherent in their code. And he did this insane thing, which if somebody had told me that it was possible, I would have told them that they were absolutely insane and that it was contrary to any biological principles, that we had these biological principles for a century already, and that they were insane. It was not going to be possible. But what this guy did is he took the flatworms and he realized that if he cut them in half, and for the first few hours after they began their process of regeneration, he basically cleared their electrical slate. He would put them into a solution that blocked their electrical communication, and he would then remove them from the solution, wash all of the chemical out, and he would produce worms that regrew with two heads. And so now you have these two-headed worms, and you're like, okay, everything I know about biology says that there's a mutation somewhere that has changed the genome of the organism, because that's the master plan of the organism that tells it how many heads it's supposed to have.
Yeah.
And then you go and...
Which is kind of like the Big Bang theory of biology.
Easily, right? It's just like, this is the central dogma. You're like, DNA, RNA, protein, that's it. And there's no genomic changes. Not only are there no genomic changes, but you can continue to cut that worm in half, and it will eternally regrow two heads. With no genetic changes, with no further like biological manipulation needed. And I'm like,
It's got the same genome, but it's because of the particular environmental conditions it's been in, it ends up with two heads rather than one.
And then eternally remembers its own form as being two-headed.
Right.
And
so,
I'm like, that is, if you had told me, if you and I were sitting here 50 years ago discussing what is biologically possible, and you told me that you thought that that was possible, if you told anyone, they would laugh you out of the room as just like the most harebrained fool that had ever spoken of science. It's like a Frankenstein monster plot.
yeah.
And encountering his work has so radically opened my conception of our shifts in understanding that are possible, where I'm like, we were dead certain for roughly 70 years that like we had biology just like locked down. And then along comes this guy who's like, no, I don't think we do. And he's right. He can show it. He can prove it. And I'm like, where else is this hiding? Can it be hiding in astrophysics? Can it be hiding in quantum physics? It's probably hiding everywhere. Because it's like,
Well,
why not? Like, is there something privileged about other sciences that says that that can't be hiding somewhere in our models? Because the models work. They're just like...
They work until they don't.
Like, they're just short of this massive piece where it's like, how do you... how do you even begin to fit that into your story of what a biological organism is without having to just rip the house down to the studs and start asking like a completely different set of questions?
I mean, obviously, like organisms still are large. Their development is largely governed by the DNA, but it's not the only factor. Obviously, right? In astrophysics, like I guess we have had changes in conception of the universe. Quite not very long ago. In some cases, for example, just 100 years ago, we didn't know if there were any other galaxies, which is weird if you think about it. I mean, like, and not just 30 years ago, like we were missing an ingredient which is now thought to be 70% of the whole universe. It's matter energy content, and that's the dark energy. But before the mid 90s, this wasn't really thought to be there. It was allowed by the equations, but people didn't think it was there. So we have had changes. The idea that things will not change. I mean, what I would say is like the better the model sort of agrees with the observations, the less likely it becomes that this was a fluke and the actual model is completely different. But in astrophysics, certainly in cosmology, right, you have this 10% level Hubble tension. What that's implying is that you managed to get like a 10% level agreement. Even then, it's not because of the measurement errors. That's actually.
Oh, sorry, can you say that?
There's a 10% level agreement.
Sorry, can you say that? Can you start back a couple sentences? Your feed cut out there for a second.
Okay, so what I was saying is that you have this 10% level agreement between the theory and the observations. Leaving aside the fact that this is actually that this rules out the model. What I would say is that even if they had agreed at the 10% level, that would still leave open the possibility that this was some kind of a fluke, that the actual model is radically different. Of course, nowadays we know that the model is different. But even if we didn't, they would still leave open the possibility. So what I would suggest is the agreements between theory and observations in the areas of astrophysics where there is agreement are typically nonetheless not that precise. I mean, there's no evidence for a problem with the theory in those cases, but the agreement is not that precise. So you could easily have like significant deviations, and it would also be consistent. That means the likelihood of someone coming up with a radically new theory is vastly higher than in biology, realistically, where you have all sorts of precise laboratory experiments. In astrophysics, where you're dealing with the an agreement at this 10% level, and that's with some of the more precise areas. In some of the less precise areas, we have a model which works, but the observation uncertainty is often larger. So it makes it much more likely. I mean, think about it this way: like just sort of 400 years ago, people were able to fit the observations of the planets and where they were in the sky, like quite well, with the Earth being at the center of the universe, of the solar system. The thing is,
it's actually a really good model. Turns out, it's a really precise model, actually.
It's a fairly good model for some things. The thing is, if the observations are not very accurate, then this will actually be able to fit the data. This is something people often don't understand. Like, there's a distinction between like a model being able to fit the data and sort of confirming the model is correct.
It also matters what data you bring in too, right? I mean, from what I understand, what was so persuasive in making that huge paradigm shift had to do with the introduction of new data about
Yes.
the moons of Jupiter and the phases of Venus and things that
Especially.
weren't really part of the astronometrical data that was fitted so nicely with these epicycles. And
In general, it's true that the geocentric model had various parameters, and these were calibrated using sort of positions of planets over time. If you try to introduce a completely different line of attack on the problem, such as actually resolving what Venus looks like, as opposed to seeing where it is, and finding its phase, and using that as an extra constraint, that kind of thing is typically how breakthroughs happen in science.
And I think that's what's happening in Nasia's example too. It's like the genetic relationships were increasingly fine-tuned. We could think of it as the mathematical models of the predictive ability of using genes to map phenotypes was increasingly secured. But people, I'm going to, maybe not exactly Nasia's example, but like something like epigenetics or something like non-coding regions.
Epigenetics is like modification on top of the sequence of DNA.
Yeah, so like people thought, oh, there's all this stuff, it's just junk DNA, it's not doing anything. And that wasn't really something that anyone was interrogating at that point in time. It was more like, we know how the genes work and that they dictate a lot of the behavior, but the things we're not looking at, we assume that they're not doing anything until we notice all of a sudden, holy crap, these non-coding regions are actually printing, non-coding RNAs and things like this that are feeding back upon the actual genome itself. And so there's these places where things that we haven't studied yet, whether it's the phases of Venus or the non-coding regions of DNA, they can radically transform the discipline overnight because it's just not been part of the conversation yet.
Well, this can certainly happen in astrophysics. The phases of Venus, of course, are like a constraint on the problem rather than changing the organism in the way DNA would. But you have other, you can have other scenarios where factors that people thought or hoped were unimportant turn out to be important. One example that should concern people is the possibility that quantum gravity effects are important in astrophysical systems. We think that they can't be, but maybe in some systems, like I know, I don't know if you have people who are advocating the Mond hypothesis, but one of the ideas behind it was that in certain environments, quantum gravity effects could become important, and that would be at low accelerations. So the idea that these things are...
First of all, unfortunately, we haven't had a Mond person on the podcast. If you know one who you think would like to talk to us, we can talk after the show or whatever, but I would love to get somebody on here. It's regrettable that we didn't get a Mond person out to the conference, but we've kind of used up our budget on flying people out at this point. But it is unfortunate because I know that it's a very serious, let's say, camp
candidate
in the at the edges of the academic discussion with respect to cosmology and astrophysics and the dark matter debate and all of that. It seems like it's certainly something we should be talking to people about.
Yeah, I think if you gotten Elena for the conference, that would have been helpful, because I don't really advocate it very much anymore, but I know she still thinks it's more likely to be correct than not.
Is there a reason why you don't advocate for it as much anymore?
Yes, that's because of the constraints on solar system scales, especially the wide binary test of gravity.
So you suspect they might not be right?
That's my opinion, yeah.
That's fair. I think that's a solid reason to not advocate.
Who's the best defender of Mond in the universe today?
I
At least on this planet.
I think Pavel's one of the strongest sort of advocates.
We had, unfortunately, we talked to Pavel a long time ago, but
Pavel told us to get a couple of Nobel Prize scientists on, and then he'd talk
Yeah,
about
he's very worried about his image. He wants to be associated with, academic stuff. He's very scared of coming on a podcast that doesn't have enough Nobel Prize laureates.
But hold on, you were what's that?
He doesn't hold much faith in the Nobel Prize typically. I mean, I doubt he's worried about. I don't know. He might be worried about his image. Maybe.
I think we had a bunch of fringe conversations because we'll sometimes go through phases where we talk to exclusively fringers, and then we'll talk exclusively to like MIT people. And I think that we picked Pavel up on a fringe swing, and he was like, absolutely not. I want nothing to do with this project. But I think a lot has changed since then.
Who's in second place?
Is it Elena?
Well, I mean, if you want someone at a more early career stage, maybe I don't know. Stacey McGaw, maybe. Although I think he wouldn't want to advocate Mon probably because he's an observer, so he tries to stay more neutral. Yeah, probably your best bet would be Elena at this point, I think, because. Though of course I asked her about this particular conference, but and she's not available for that. But I think she is one of the best advocates for it, who has a very good understanding of the evidence.
By the way, I just realized we got way deep. We just got way deep in the nerd woods. What the heck is MOND? First of all, like I think people, yeah.
She has a very good grasp of the evidence, but has come to a different conclusion, which is fair enough. But yeah, the MOND hypothesis is basically the idea that if you originally it was motivated to explain why galaxies rotate faster than expected in their outskirts. So as you go further and further from the sun, the more distant planets orbit the sun slower. You would think it's the same in the galaxy, that once you're outside the bulk of the mass, as you go further and further out, the rotation speed goes down, but it doesn't. It stays flat. And one possibility is to modify the law of gravity. So basically, when gravity is very weak, it decays inversely with the distance, rather than inversely with the square of the distance. That implies a much slower decline with distance than in the Newtonian theory, which will cause the rotation curve to be flat. So that's the basic idea.
It's kind of like it's kind of an alternative to dark matter, because it seems like dark matter arises out of the need to plug all of that missing mass so that you can flatten this curve essentially. Well,
it's a missing gravity, I would say. But yes, dark matter is obviously one way to explain where all this missing gravity is coming from. But the other way is to say that it actually just comes from the visible mass with the modified law of gravity.
It's interesting that you. Okay, I can follow that. Yeah.
And are you more in favor of the dark matter, or do you think that there's something else that might be responsible for this?
I think that there might be some other explanation, but at the moment, I'm of the opinion that the missing gravity in galaxies probably comes from dark matter. But I wouldn't be very confident about that. I mean, I think that's the most likely explanation, simply because there's a lot of evidence. So certainly, even when I advocated for MOND, I thought that this was the correct explanation in clusters, that you had dark matter there, because MOND can't really explain a similar kind of problem that arises in galaxy clusters. Now I think that since you're on the slightly larger scale of galaxy clusters, you probably need dark matter anyway. The easiest solution is to assume that this is also able to cluster on the smaller scales of individual galaxies and form halos surrounding them. But this causes some problems, and I'm not completely sure it's the right approach. I just think that's the most likely approach.
Well, I mean, it's certainly scary to posit that there's some substance that you can't see that's doing all of this effort in the universe.
I agree. I just think it's difficult to. I just think you can't really explain the observations with just the visible mass. that this causes very significant problems.
I have the world's dumbest question.
But yeah,
Forgive me for asking, but for something like a galaxy, what is it possible that there's stuff at the edges that's normal matter, but it's just cold and dark, and it's like dead planets and things that have been just frothed out from the galaxy?
The great galactic garbage dump.
Yeah, like, is it because I know that it's really difficult to see things that are small, cold, and dark.
That's not quite true. This possibility was considered for a while, but the reason why we know this isn't right is because these objects would occasionally pass in front of a background star, and it would gravitationally magnify the background star. So we'd have a so-called gravitational microlensing event.
Even if it was little? Like, even if it was tiny junk?
So we're sensitive down to, certainly down to planetary masses, almost down to the Earth mass, which will create a microlensing lasting sort of order an hour or something. So it's we're sensitive to a very wide range of masses. Certainly any kind of any kind of star, even if it's, because this is based on its mass rather than its light, it could be like completely dark. But if it's around 0.1 solar masses and like a compact object, and makes up most of the dark matter, we can rule out that possibility.
Interesting. When it comes to seeing the gravitational microlensing of something that's on the order of the size of the Earth, that's just like looking out to like an exoplanetary system and being able to see some kind of transit that causes a microlensing event in the direction of observation, or like how do we know that? Indranil, I feel like we've just spent the last 2 hours just putting you on the spot about things. You've been such a good sport.
How you mean? You're asking how we can find an Earth mass?
So I was like, why can't they be cold and dark? And you're like, well, they can't be cold and dark out there because we know that even small Earth-sized objects cause gravitational microlensing that lasts some amount of time. And I'm like, so we've seen that in exoplanet systems, or we see that in the solar system. Like, how do we know that that's? Do you know the observations that have been made of?
Well, you look at stars typically towards the galactic center, or if you're trying to look at the halo, you often look at like towards a large Magellanic Cloud, which is quite sort of far out compared to where the dark matter would need to be anyway. And then you can calculate, of course, how long the microlensing event should last for any particular mass. We have seen microlensing caused by planets. In some cases, free-floating planets as well. So not always bound to a star. But we have also seen microlensing events created by exoplanets. But in those cases, obviously, the actual parent star would create a longer, sort of perhaps year-long microlensing event. And you'd see a little additional blip on top of that when the planet passes in front of the background star. So we've seen these kinds of things, but more importantly, we've seen too few for the dark matter to be made of compact objects, unless they're like below an Earth mass or something.
Interesting. Okay.
This was like the Machos hypothesis at some point in time?
Yes, exactly.
I love these names so much. All right, equally stupid question. What about other cohesive mechanisms? Like, we had this dude on the show like more than a year ago, who was at Stanford. I'm blanking on his name, but he was studying how galactic magnetic fields are used to organize the evolution.
Enrique Lopez Rodriguez.
Thank you. I love your memory. Enrique Lopez Rodriguez. He was talking about the new field of galactic magnetism in the evolution and architecture of galaxies. And I think at the time we spoke with him, he was one of like 30 people in the world studying this kind of thing. And
and every question was, he was basically like, we don't know yet. We haven't looked. We don't have the data.
Well, the magnetic fields they're not simple bar magnet systems. There's all sorts of turbulent, chaotic eddies, and it's very complicated sheaths of different polarity on top of one another. And it's like this very complex patterning system from what I recall. And I'm just wondering if there's any possibility that other more mundane forces might be contributing to the cohesion of the galaxy as a whole, where that might save us from introducing new magical substances that we can't see. Because that's hurt us in the past,
I understand. Like one issue I have with this kind of hypothesis is it's designed primarily for the rotating systems, but you also have a similar problem in sort of dispersion dominated or pressure supported systems, and these are the dwarf galaxies where they're not rotating, but the velocities of the stars are random, and it's basically these random motions create a sort of pressure which supports the dwarf against its gravity. So in those cases too, the pressure you have is much larger than would be needed to balance the gravity if you just had like the visible mass and standard gravity. So in short, we know that there's more gravity than is expected in the dwarf galaxies, which are not even rotating. This is also true in like more massive elliptical galaxies as well. So you have
you're just, what's this pressure? Just solar wind, basically?
No, this is not real pressure in the way people think about it. This is like if stars sort of move randomly, that creates an effective kind of pressure. Essentially, the fact that the orbits are somewhat elliptical prevents them from sort of all collapsing into a point, if you will. So it's a kind of effective pressure that arises. But this process only creates like a certain amount of pressure. So if you had like if a system was in equilibrium against gravity, and you suddenly raise the amount of gravity a factor of 10, it obviously would collapse it. But yeah, it's a sort of a dynamical pressure, if you like.
Yeah, it is a real pickle. It is a real pickle.
Galaxies too.
Yeah, when I think about these substances that are hypothesized, like dark matter, it reminds me a lot of some of the earlier substances that we've had in science. Just the taste of it, the sound, the proposal sounds to me a lot like the caloric theory of heat or something, the phlogiston theory of heat, where you have this fluid that is flowing through the substances responsible for their temperature variations and so forth. And then eventually somebody realizes like, oh no, it's just actually this kind of mundane friction process where the atoms are kind of grinding up against each other or whatever. And, what's funny about that story is that once again, kind of like with the Ptolemaic system we were discussing, the mathematics for the flow of this fluid work perfectly. It's a fantastically predictive model of heat transfer to treat it like a fluid, right? To treat it like this kind of dark heat matter stuff. And so I wonder if, not to criticize dark matter, but to say, is this just a phase that we go through when we're approaching a new phenomenon that we don't understand at the fine-grained level? In other words, the atomic theory, our atomic knowledge at the time of this caloric theory was essentially non-existent. It was very nascent, right? And so as we put together a better model of the rest of the universe, and we understand more nitty-gritties about mundane phenomena, then we're able to revisit some of our models where we'd kind of put this placeholder magical fluid in, and then that's just kind of how science is done, is what I'm kind of asking. Is that just a normal expectation? Like, maybe this dark matter will work to solve the problem, and then at some point down the road, it will be uncovered, the real roots of that, which isn't necessarily some undetectable substance. It's just some process, maybe an atomic process, maybe a subatomic process, something that we haven't fully understood at this point in the short history of science.
I would say that's possible. I mean, it's certainly could happen. I mean, especially with the caloric theory, like one reason it sort of worked to some extent is because, like, I mean, it's not caloric that's flowing when heat moves from a hotter to a colder body, but it's like energy flowing. But in many ways, like, that can be captured by fluid dynamics equations, even though it's not a real fluid flowing, it's like the energy. So in that sense, yeah, it's possible that the equations governing the dark matter that people have written down are similar to what the actual equations are, but the actual substance is not dark matter. There's nothing there. It's just the visible mass. This kind of thing is possible, in my opinion. In fact, just now I was at a talk by Milgram for like a couple of hours, where he was showing the results regarding the very, very tight correlation between the distribution of visible mass and the rotation curves, which is observed, which actually does lend strong sort of support to the idea that it's just the visible mass that's there, and we need to sort of modify our understanding of how visible matter works, in this case probably how gravity works, but certainly how some aspect of how matter organizes itself on sort of kiloparsec scales. So it is possible. I certainly wouldn't rule out the idea that there isn't really any mass there. What I would suggest is it's difficult to explain everything with just assuming the visible mass and creating some extra way in which it can interact. I mean, because one thing to understand is that you have, for example, in a galaxy, you can have a photon going past it, and it gets deflected by the galaxy. There's an anomaly there too, in the sense that the photon is deflected more than it should be if you just have the gravity of the visible mass. So it's hard to understand, like, how the photon could be responding to any other forces. Photons basically just follow straight lines in the space-time. So what is going on is there is additional space-time curvature around a galaxy. It's not simply the stars and gas are circling around it, orbiting it faster than predicted. The galaxy genuinely has distorted space-time more than it should have done.
I think it's really exciting. I mean, this is kind of, if it is a moment akin to the transition to a molecular theory of heat or whatever it's called, that
would be super exciting.
It would be awesome. It'd be like we're one Boltzmann away from having like a completely new physicalization of the situation. It's just, it feels like we're potentially on the precipice of something really brilliant.
Sometimes it does feel like that, especially sometimes people do propose sort of statistical descriptions, assuming, if you like, well, making some assumptions about what the fundamental ingredients or atoms of space-time are like, and saying that, okay, but I didn't fully understand them. So what it is, like, I treated them in a certain statistical way, and we managed to derive all these results that are observed and often have been explained in other ways. And that, of course, will open a major new sort of line of investigation if we can say that, okay, now we understand space-time statistically. Well, nowadays we don't understand it at all, of course. But imagine if in the future people understood it statistically, then it would pave the way to understanding it at a more fine-grained level, what it actually is. It would take, of course, like, we're not very, I don't know how close we are to even understanding it at a statistical level. But certainly if we got that would be a huge breakthrough. It would take like generations to unpack the full meaning of such a breakthrough as well. But if somehow it could be demonstrated that it had a certain structure, and yeah,
I mean,
really quite wrong.
It's at least food for thought. Like, yeah. So do you want to tell people about this conference that you're putting on?
Oh, yes. This is part of the National Astronomy meeting in Britain. There's a parallel session there on the Hubble tension. So we're interested in talks related to it in some ways. So it could be observations, distances, and redshifts, but also perhaps observations of the very early universe of the CMB, modeling of it. Also theoretical approaches, if people have ideas on how they think the Hubble tension should be solved, they want to present it. We're especially encouraging early career researchers to come, though of course anyone can present there. So yeah, it's about this. It's and any kind of ideas are welcome in principle.
Are you still accepting abstracts for that?
Yeah, exactly. We just opened the call for abstracts. It'll be open till the end of March.
And was there a website where people can find out more about that too?
Yeah, it's the UK National Astronomy Meeting. I'll send the link after if you want.
Right on. Well, we can put it down in the show notes.
Definitely. I mean, I think that it's an exciting time to be alive because there's so much left to be figured out. And I think that anytime that there's a massive change in the way that we understand some system, it suddenly opens the floodgates to so many new ideas and so many new ways of perceiving nature that I think is kind of what we're all after in the sciences to begin with. And I don't know where astrophysics, astronomy, and cosmology will land, but it seems clear that there is a feverish atmosphere of people trying to figure out where exactly it should go. And so it's very cool to have a front row seat to that.
It's a really exciting time, and one in addition to the failure of the standard cosmological model, which is obviously a crucial aspect. The other thing is the improvements in technology and new instruments coming online. So what used to happen it was already exciting enough when sort of 3-4 years ago people actually identified the Hubble tension. But back then there was maybe only one technique that was sort of sensitive enough to see it in the first place. Nowadays, what's really exciting is that many different techniques are in principle sensitive enough to see a 10% level mismatch with what you predict in the standard model, but not all of them actually see such a tension. Some do and some don't. And by looking at the patterns of these people see like a discrepancy with λCDM, these people who are equally accurate don't. They're looking at a slightly different aspect of λCDM, but there seems to be no problem there down to the percent level. That's super exciting because in some models for the Hubble tension, that's fine, it makes sense. But in some other models, these other people should also have seen the same 10% level tension. So you can sort of discriminate where the Hubble tension is really coming from. So this is what's exciting. When we're moving from an era now of detection of the Hubble tension to characterization of where it's coming from. It's like if you have some sort of alien megastructure, you see it as one pixel and just enough to kind of know it's there, versus seeing like an image of it, a low resolution image, or seeing its light curve over longer periods. We're moving to an era of characterizing this structure that it can't be explained naturally, for example. We're moving to...
That would be a very different conference, I must say.
Well, it's just an example of something that couldn't be explained naturally. The same could be said of the expansion rate of the universe with the current theories. Something gone wrong. But we're moving to just like we're moving from just convincing people that there is such an anomaly, which most people accept by now, to characterizing why the problem might be, which aspect might you adjust. A lot of the proposals to adjust λCDM are not necessarily proposing any new sort of fundamental microphysical model. Indeed, my idea of the local void isn't proposing something like that. It's just saying, like, in general terms, this is where you need to modify things. So whether the modification should be sort of prior to recombinations, as you were suggesting earlier, or it should be in the late universe or somewhere else. So a lot of it is just very phenomenological, just trying to say like roughly how could we tweak things. So one analogy is like if you had the anomaly in Mercury's orbit in the past. Some people did try to just tweak the gravity law a little bit and solve the problem. Very few people thought that made sense. Mostly the consensus was that you just needed like an extra interior planet. But actually tweaking the gravity law a little bit was much closer to what actually happens than any of the other proposals. So I feel like in that scenario, people did not make as much progress as they should have done because, I don't know, maybe the technology is more limited. But also, if people just realize that that provides a better explanation for the observations. I guess the problem is there's only one planet where they had such an anomaly. If there had been other very close-in planets where they could see, for example, a planet that's orbiting like twice as fast, the anomaly would theoretically have been 4 times larger because it scales with like v squared. So if they'd seen that, then they might have realized, well, hang on, this anomaly is caused by some actual breakdown of our understanding of gravity that kicks in these regions. And they might have tried to understand why that was. So I feel like we're in an era where we're trying to not only see that there's an anomaly, but sort of see the patterns of the anomaly. The anomaly sort of becomes larger in these scenarios, or in these other scenarios, the anomaly isn't there. So it's kind of like that.
I think that might actually be this really incredible time where people have an opportunity to go back and review old proposals. Because I think that if you look at something like even the atomic theory of heat, like the idea of atoms had been floating around for a really long time. And then a bunch of things clicked into place in order to actually demonstrate that these things that we're seeing are related to the material composition of everything and that heat is the motion of those things. And all of the sudden you get from this ancient idea, right? Like Democritus was talking about this like 4,000 years ago. And so you have a what's that?
Not quite, but
No?
that's fine.
When was he?
Probably
like
like
2000
2000 or something.
I thought it was like 2000 BC.
I mean, Democritus's original writings don't survive, from what I understand, but others wrote about him. I think that he's placed in like somewhere in the first millennium BC, like 500 or something.
Really? Okay.
500 BC approximately. Yeah.
I'm really, 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 really bad with dates.
It's a really old idea, atoms, right? But it took a lot of data before it became a serious scientific proposal.
But I just and I think that there's something about this phase of the collecting of the data where everybody's like very obsessed with the process, where all of a sudden people start to look around and they're like, well, hey, hold on a second. We actually have quite a lot of data. And now our challenge is to be able to figure out how all of these pieces fit together and what are the old stories that we used to tell? How do they help us transform our understanding? Because if you look at it, to go back to the biology example, if you look at Levin's work, like there are people who have pointed to what he's demonstrated unequivocally for the last like 150 years. And so you can trace the genealogy of the idea back, but he was the first one who was actually able to come up with a compelling laboratory experiment that demonstrates it.
Show it.
And I'm like, the history of science is littered with the people who came up with an idea before it was their time. And so I think that that's what's really exciting now, is that like we don't have to depend just on our minds. We have the benefit of history and the benefit of everybody who came before us to be like, these are the ideas that let us shape the future a little bit. And I think it's very cool.
It's definitely entirely possible that an idea that people came up with in the past and perhaps didn't pursue for whatever reason turns out to help address some of the issues cosmology is facing now. And that's entirely possible. But yeah, sometimes people do worry more about the process of collecting the data without like reviewing it too much. That's actually partly why I'm also like guest editor on a special issue for Galaxies on the Hubble tension. We sort of accepting contributions related to any kind of aspect of the Hubble tension, and it'll go through peer review. But it's designed primarily for reviews of the evidence rather than for new research or on new measurements. It's also like I suspect for a lot of researchers as well, it's like less controversial in many cases to be collecting measurements. I mean, just recently we had a talk by someone who was talking about like this dark energy survey where they like take observations of supernovae, and she dodged any issues associated with calibration of the supernovae. She was like, she only works with the uncalibrated supernovae, and thereby like her work has kind of nothing to do with the Hubble tension kind of thing. Which I mean, we were discussing this afterwards. In any realistic proposal to address like some of the tensions she was talking about regarding the shape of the expansion history, which is all you can constrain without an absolute calibration. In any realistic proposal to like address anything related to the shape of the expansion history, the present expansion rate will inevitably be affected. So so she wasn't really able to shield herself from the controversy about the Hubble tension in the way she was hoping for. But she has largely shielded herself from this controversy. That's certainly true. Whether that's a good thing is perhaps another issue. Considering,
But it's a clever, yeah. I mean, it's a clever survival tactic, right? Where you're like, I just collect the data, man. Like I'm filling out the rows in the spreadsheet.
It's funny because when I many years ago, some of the first labs I worked in were cancer research. Cancer research is notoriously impossible to translate from the laboratory into the clinic, right? It's something like a 90% failure rate. You develop something that you can cure cancer in mice. Like we've been saying, you can cure cancer in mice for many decades now, but getting it into the patients is a whole nother matter. And I always thought like the main problem with that was that you had the same people doing the experiments who were analyzing the data. And it seems like astronomy has solved that problem for itself just by virtue of the fact that they have really expensive instruments they have to share. So I think that's pretty cool. I mean, it's a fortunate system that I think lends itself towards progress.
Yeah. I mean, we have there's obviously a lot that's left to talk about, and I'm really excited that you're going to be with us in Portugal and that we get to pick your brain in person and that you're really trying to figure this stuff out. I think that these are really deep questions that'll help us see everything a little bit more clearly, and I'm glad that we found you.
Thanks. Yeah, no, it's a really exciting time to be trying to address these issues in cosmology and in physics more generally. Like certainly we do benefit a lot from people trying to make the data usable outside the whatever question they were trying to answer. That's certainly valuable, but yeah, in general, it's a really exciting time to be having access to all these new measurements, and also telling people which kinds of measurements may help in the future.
Heck yeah, I'm excited to hang out in June. So we're gonna see you. I'm gonna say very soon. I know it's like a quarter of a year away, but I'm really excited to get you together, especially with some of the other folks we've had on the podcast, and really chop it up about what comes next. So yeah, Indranil, I think we will not take any more of your time today, and I really appreciate you coming by, but there's so much more to unpack, and fortunately we have time in the future. Is there anything else you wanted to plug before we let you go?
Well, I think I just want to remind people about the conference in Durham and the special issue for galaxies, which should be a good chance to review some of the latest evidence, share your thoughts maybe on where you think the Hubble tension is coming from, and try to back that up. Well, so I'll send a link regarding this to advertising, like a blog post on Pavel's website where we'll explain all this a bit.
Cool. Yeah, great. We'll link it down below.
For sure. All right, Indranil. Let's put a pin in it. We'll see you again soon.